In this video, we're going to look at some exceptions to the octet rule. So in previous videos, we've been looking at things that pretty much follow what we've been calling the octet rule, that most atoms prefer to have 8 valence electrons available to them when they're bonding, of course with the exception of hydrogen, since it can only hold 2. But there are actually quite a few things that don't follow the octet rule. It is more of a guideline than an actual rule. And essentially there are two different ways that we can have quote-unquote violations of the octet rule. We can either have too few electrons or too many electrons compared to that 8 that we've been aiming for thus far. So the first version, having less than 8 electrons, is referred to as an incomplete octet. So anything where the best structure you can draw has fewer than 8 valence electrons is said to have an incomplete octet. For the purposes of this course, at least, these exceptions will only occur on the central atom. The peripheral atoms will obey their respective rules, so usually 8 except for hydrogen. So with incomplete octets, these usually only happen if they're absolutely necessary. They're not terribly common, really, but they do happen occasionally. And the only kind of exception to that is boron, which actually prefers to have only 6 valence electrons compared to 8. So you'll usually find a central boron atom has 3 bonds to it, which gives it a total of 6 electrons available to it, rather than the preferred 8. So for example, if we look at the structure for boron trihydride, BH3, this would have boron as the central atom with 3 hydrogen atoms around it. Now in this case, there isn't actually anything we can do. There is no way to get boron to a filled octet here, since none of our peripheral atoms have any lone pairs. We couldn't create a double bond or anything in this situation without adding too many electrons to this structure. But even if there were lone pairs on those peripheral atoms, the preferred structure would still look like this, with 3 single bonds, giving boron only 6 valence electrons and that incomplete octet. So the incomplete octet is typical for boron. You should be aware of that exception. Otherwise, incomplete octets are pretty rare, and they only happen if you have absolutely no other choice. And we'll talk a little bit about why boron prefers this in a later lesson, but for now, just be aware that that's a thing. So what you will come across much more commonly is known as an expanded octet of more than 8 electrons. So we've been talking a lot about this octet rule, but many elements can and regularly do have more than 8 valence electrons. So for many things, 8 is kind of more like a minimum than a specific requirement. So you will see expanded octets pretty commonly. But it's not always possible. So not all elements are capable of having an expanded octet. What needs to be true is that an element must have a d subshell available in its valence shell. We know from our understanding of the structure of the atom that the d subshell doesn't appear until the n equals 3 shell. So that means that the valence shell of an element must be the n equals 3 or higher in order for it to have an expanded octet. So what this means for us is that only elements in periods 3 through 7 are capable of having an expanded octet. That's most of the periodic table. Remember that the periods are the rows, so the top 2 rows, periods 1 and 2, that is the first 10 elements cannot have an expanded octet. It is physically impossible for them. The rest of the periodic table, elements 11 through 118, all can, under the right circumstances. If either you just have more electrons and you need some place to stick them, or, again, something we'll look at in a later video, if it's actually more stable in some cases for a central atom to have an expanded octet. So most of the periodic table can do this. You will see it really commonly for things like phosphorus and sulfur, especially, are probably the most common elements that you're going to see in this course, having expanded octets, but there are loads of others that can do it as well. So for example, SeCl4. So if we take a look at this structure, selenium, is in group 6. Chlorine is in group 7, and there are 4 of those. So 4 times 7 is 28, plus 6 is 34 electrons that we need to place in our structure when we are drawing this. So if we put selenium is our unique atom, so that one can go in the middle with the 4 chlorines arranged around it. Our next step is always to fill up the peripheral valence shells. So we'll add 3 lone pairs to each of those chlorine atoms. And then our next step in the process is if we have any electrons left, they go on the central atom. So at this point we have 8 electrons, 2, 4, 6, 8 electrons around each of our chlorines. 8 times 4 is 32. So we are 2 electrons short. Those 2 electrons have no place to go but the central atom. But this feels a little funny when you first do it, because if you look at the selenium atom before we add that lone pair, we already have 2, 4, 6, 8 electrons. It has a filled octet. So when you're first starting out and you're like, octet rule is the thing, it feels a little weird to add more. But selenium is in period 4. So it has that d orbital available. It's able to accommodate those extra electrons. So the selenium here ends up with 2, 4, 6, 8, 10 total valence electrons, and that's fine. That's not a problem. But that is what we mean when we say something has an expanded octet, that it ends up with more than 8 valence electrons to it, and again, that's fine for a lot of things. So all of our other atoms here, the chlorines, each have 3 lone pairs and have access to the electrons in this bond for a total of 8. The selenium has those 4 bonds plus its lone pair for a total of 10. So when you have extra electrons to place, don't be afraid of expanded octets, as long as your element is able to accommodate it.